Hello. So today we're going to talk about shapes, a new topic that we haven't seen before in the course. So we previously spoke about various aspects of the semantic web in terms of data, logic, query, and links. So what's missing from this picture, right? What about data quality? So what about the quality of the data that we're modeling as RDF? Are we modeling the data completely? Are we modeling the data properly? So one of the benefits of graphs that we spoke about in the second class is that we don't have to impose a structure or a schema from the start. Of course, the downside of that is that we don't have a structure, a schema imposed from the start to be able to validate and structure our data. So we discussed the idea that somehow there's this emergent structure, but maybe we can formalize this at some point when we've collected quite some data. So maybe we could have two pros, right? Maybe we don't have to impose a structure or schema from the start, but when we like, we can impose a schema anytime. So there are different forms of schema, and we already spoke about RDFS schema, which I think is probably not a good name for it. It's more of an ontology language. So I'll describe or discuss why RDF schema is perhaps not enough for the semantic web. But the question is, how can we define and impose a schema for graphs? Aside from RDF schema, we have this option of using shapes. And the main difference is that shapes can be used for validation, for defining the structure of RDF graphs. So what do I mean by validation? So we have some data here about Academy Awards, Academy Award for Best Picture and Academy Award for Best Director. So we see that Parasite won both of these, and in the case of Best Director, the award is also associated with the person who directed the movie. So the question then is this graph complete? Does it have errors? And how do we even define completeness and errors? So in some sense, some domain expert is going to have to define some notion of completeness. Maybe, for example, with respect to an application, maybe an application requires some minimal data to be able to function, for example. So is it complete? Well, we see maybe there's some details missing. Maybe we'd like to have a name for this. Maybe we'd like to have a name or date of birth for the director and so forth. Okay, so what we have here is essentially a shapes graph. So what it describes essentially is a structure. And what that structure is, it's composed of shapes like award, Academy Best Picture, person and movie. And each shape has some constraints associated with it. So we say an award should have a year, it should have precisely 1 year, and the data type should be G year. It should have one or more names, and they should be language strings. So they should be strings with a language tag. We see some inheritance here where Academy Award also inherits the constraints of award, and so too does Academy Best Picture and Academy Best Director. Okay. Aside from that, we have these other types of links where we see, for example, an award can have 0 or many judges, and those judges should be people or persons conforming to the person shape. And we see that movie should have one or more directors conforming to the person shape. Okay. So how does it look with respect to this graph here? So if we take this graph here, question is, does it pass? And the answer is yes. So what's missing at the moment is that we've yet to define a target for the shape. So we don't know somehow like what nodes here correspond to what nodes here. So essentially we're not checking anything. We've yet to say that, okay, we should use this um, awards shape, for example, to validate the instances of award. So we need to define target. So we can do that by simply defining, for example, that movie shape will target all of the things of type movie, all of the instances of movie. In this case, for example, we see that Parasite is of type movie. So this is targeted by the shape. Now we expect that, okay, well, let's ask the question, does it pass? We expect Parasite now to have a year from G year, which it does. We expect it to have a short. Is it a short movie? Yes or no, true or false. This is optional, so we have 0 or 1, so that's okay. We have 0 in this case. And name, we expect to have one or more names. And we see that we have one name here with the language tag. So locally, the shape is satisfied. Next, we expect it to have at least one director. So we see that that's the case here. And that director has to satisfy the person shape, which means that this director here needs a name and a date of birth. And we see that it has neither. So we say that it does not pass because this director does not satisfy the person shape. So we're missing a date of birth and a name for the director. Okay, so let's say, for example, let's suppose that we define that it requires 0 or more directors. So the question now is, does it, if we relax from 1 to 0, does it satisfy the shapes graph? And actually, this sort of depends on how we define, but typically, what we're going to say is that this is not, this is a cardinality. The cardinality is independent. It's not a qualified cardinality. We can define that actually in the languages. We'll see that later. But we're going to assume here that the cardinality is separate from the constraint that all directors satisfy person. In that case, no. So despite the cardinality, any director must still be a person. Since it has a director, that director must satisfy the shape person. It doesn't, so no. Okay. So last but not least, we could consider adding the missing information so that the director satisfies the person shape. So we can add a name and we can add a date of birth. And we see essentially that these have the expected types, the language string and a date. So we should be good. Will it validate now? So remember again that all we're doing here is targeting the movie shape to instances of movie. So we start with parasite and we check all of its local information. Then we check the director to make sure it satisfies person. And we see that we're now good. Okay. So this is the rough idea. Yeah. This is the idea of shapes. So why introduce something new is the first big question, right? So what's the difference between this and RDFS and OWL? We already saw we could define cardinalities and ranges and all sorts of cool stuff with RDFS and OWL. And what's the difference with SPARQL? So with respect to RDFS and OWL, we could define something very similar to what this shapes graph describes. So we could say, for example, that an award is a subclass of all of its years are from the data type G year, all values from, sorry, that should be capital F. That it has 1 year, precisely 1 year, that it has all its values for name or from language string, and so forth. So we can define somehow something very similar to what we see here in RDFS and OWL. So what's the difference? Why do we need shapes? The thing is that OWL applies interpretations and it reasons about those interpretations. So what do I mean about an interpretation? It doesn't reason about nodes in a graph and edges in a graph. It reasons about things, about movies, about people. And it essentially adopts two philosophies. One is the open world assumption, where data might be missing. Okay, and that's not, a problem. We can sometimes even infer the data that are missing. And we don't have a unique name assumption. So what this means is it's quite difficult in OWL to detect missing data because we just assume the data are incomplete anyway, so we're not going to flag or give an error if we're missing data. Or duplicated values, by which I mean, for example, having, you say, for example, that a person has at most 2 biological parents, and then you find a person with 3 biological parents in OWL, you would assume that 2 of those must be the same person, the same entity. So it's difficult to validate data, right, with OWL and RDFS and all. What about SPARQL? So in SPARQL, we don't apply interpretations. If we, for example, query for how many biological parents that person has, then we would get 3 because there are 3 nodes in the graph. Okay, we're not counting people, we're counting nodes with SPARQL. So actually with SPARQL, we have the right semantics. It's just that it's going to be a real pain to define these sorts of constraints in SPARQL. So it's not easy, even, looking at the what's here, it looks pretty complicated, but even to come to this solution, to come to this sort of query is not straightforward. So what we're trying to do here is write a query to find constraint violations. So, and this is just for the movie shape. So we get all the movies. This is essentially the target. Okay, and then we optionally try to find years if they're available. If we find that there's no year available, or the data type of some year is not a G year, or there exist 2 years that are different, that means that there must be multiple years and we expect at most one, then that's going to be a constraint violation. Then for short, we have 0 to 1. So we can at most 1 again. So we get optional short 1, optional short 2. So first we have to make sure it's bound because it's 0. Okay, so if it's not bound, then we're not going to return that, right? So we make sure it's bound, and then we have to check to see. We're again looking for violations, so we're going to check to see if it has a data type that's not Boolean, or it has 2 different values for short, and so on. So we do the same for name. However, we're still not done here. This isn't even the full query yet, because all we've done is kind of verify the local constraints. We haven't actually checked the director person constraint yet. So that's another block of query that's required here. And somehow you get the sense that, this is not really ideal because we're copying in constraints here. And if this pointed over here, then we'd have to copy in more constraints. And okay, maybe we could break it down into different queries and so forth, but it's quite difficult to express these sorts of constraints in a sort of in a component-based way, break it down into different shapes and define the constraints for those, and then link the shapes according to the relations that exist between the entities for those. So we see that SPARQL's not ideal. I mean, we could do it in SPARQL, and actually many times SHACL implementations. Sorry, what's SHACL? I'll have to explain that in a moment. I'm kind of jumping ahead with the logo, but it's a standard for expressing shapes. So some implementations of this standard will translate to SPARQL queries, but we don't really want to have to express our constraints this way. So we have the correct semantics, but it's just difficult to express these types of constraints. So SHACL is shapes constraint language. There's essentially 2 main shapes languages compatible with ODF. I'm going to speak about SHACL mainly. So SHACL is essentially the answer to the question, how do we actually write these things down? How do we define these shapes graphs? Yeah. So SHACL I'm going to focus on because it's a W3C standard. It's one of the more recent standards in the semantic web from 2017. I wanted to teach this class last year, but with the complications at the end of the semester last year, we didn't get to the class. So, okay, we want to write down these shapes graphs. So how do we do that? So we'll have a look at this example first, and then we'll discuss a bit more about the language. So SHACL, we have different syntaxes for SHACL, but I'm going to focus on the RDF one based on Turtle. So the first thing we can do is we can define the person shape. So we say a person is a node shape. So we have node shapes and property shapes. So the difference is that property shapes here, this link node structure here, this is all a property shape. A property shape takes a path. Okay, so let's return. So we say we have a shape person, there's a node shape. Okay, and this SH is the SHACL vocabulary. And we say that a person has a property shape, which is a path on name. We want to take the data type of language string, and we want almost one, at least one. So we have at least one name, and all names are of data type language string. Here we say that a person has at least one and at most one date of birth, and the data type is date. Okay, so we've pretty much covered this, this shape here. So what about movie? Movie, we have the same thing. We define in a very similar way all of the sort of internal constraints here. What's more interesting is this connection we have, right? So we have a director path, And instead of like specifying a data type or some local constraint in that, what we say is that the directors must satisfy the node shape person. Okay, so we're somehow linking back to this person shape that we described earlier. And each movie must have at least one director. Okay, so this is how we form this link. So we link to a node shape, which is already here, person and person here. So this forms the link in the shapes graph. So what about the target? So we have a number of ways of defining targets, but the perhaps conceptually most straightforward is target class. So we say that the movie shape, which has the namespace S, targets the movie class, okay, with the default namespace. So this allows us to say that somehow the instances of movie in the data are targeted by this movie shape. Next, we move to award. Very similar here. Again, this link here, we see we have path judge, and we say that it must satisfy the person shape. Since we have 0 to many, it's sort of the default cardinality. We don't need to define a constraint on that, right? It's the most general case. We have Academy Award. So what's interesting here is that we have an inheritance. So how do we express that? We express that with node award. So we see that directly on the node shape, we say that all nodes here must satisfy also the node shape award. So the difference is that this is not inside a property. It doesn't have a path associated with it. It means directly that the nodes targeted by the Academy Award shape must also satisfy the award shape. And then we have something very similar to what we saw before. We have lots of different links here that we define. For example, we say path nominated person, and we say node must satisfy person. Okay, and we have 0 to many, so we don't define a cardinality. In the case of movies, we say that there must be at least one movie nominated and at least one movie that is won. And finally, Academy Best Picture and Academy Best Director, we just simply do as we saw before. We say that each node targeted by this shape must also satisfy the Academy Award node shape. So hopefully that's relatively clear. So that's a high level kind of overview. So we can dig a little bit more into the language and look at what's in there. So the first thing we need to talk about is how we can target nodes in the graph. So we have our shapes and we need to specify, excuse me, we need to specify the targets. So we can target based on instances of a class, we can target the domain of a property, so we can target all subjects of some property, right? Win movie. We can target all objects of something, so we can target all objects of date of birth, for example. We can target a specific node as well, or specific nodes. If we combine on one node shape, we can add multiple targets, and in that case, it will be the union of all the nodes for that. Okay, so if we define multiple targets, then we take all of the nodes that are targeted by at least one of those targets. So targeting range, we already saw targeting instances of a class. So how does the targeting range work? So we'll just say we're going to target the objects of win person. Okay, so in this case, we define that the person shape, we're going to target it to the range of win person, the objects of win person. Okay, and we define then the constraints on person. So if we apply then this shapes graph to this graph here, we see that we're targeting John Hu. I'm not sure how my pronunciation is. Jun Hu. So what are we constraining? Must have at least one name. That's a language, and all names must be language strings. Must have precisely one date of birth with XSD date. So we see we're good here. So is it valid? Yes. Right. So we see that we satisfy all the internal constraints and there's no outgoing dependencies, right? So we're good. What about if we target, for example, award to type award? Okay, so here we target class award. What's interesting about SHACL is that it has some limited inference, very, very limited, I would say, but essentially you can traverse subclass of edges in RDFS. So we're targeting instances of award, and we know that these must be instances of award indirectly because they're of type something that's a subclass of something that's a subclass of something. So actually these are targeted. These two awards, award for Best Picture 2020, award for Best Director 2020. So we're going to target these, and then we're going to apply the constraints. So we expect a year, precisely 1 year. So we see we're good, and we expect at least one name, and we see that we're not so good, right? We're missing names for these awards. So this is not going to be valid, right? What's important here is that SHACL can target subclasses, so we can somehow close the subclass hierarchy. Okay, so it's not valid. These two nodes fail to satisfy the shapes that target them. So, okay, we've seen targets. So we mentioned that property shapes require a path, okay, and that somehow defines, based on the current node, how we traverse to the related nodes to check them. So we have different ways of defining paths that are essentially the same as property paths in SPARQL, without the negated property sets, but they're quite rarely used in SPARQL anyways. So essentially we have pretty much the same paths as in SPARQL. So but we have to express them in Turtle, right? So we have a simple property. We have an inverse path E, and this E can be sort of filled in with anything else right here. So it's any other sort of expression we have here. We have E followed by F, okay? We have an alternative path, so this is E or F. We have 0 or more of E, and this is written as E star in SPARQL. We have 1 or more path of E, which is E plus in SPARQL. 0 or 1 path of E, which is E question mark in SPARQL. Okay, so essentially we have a way of writing down property paths, and we can use those. So a slightly complex example here, perhaps. What we're saying is that the shape Academy Best Director, and this is the award for Academy Best Director, the movie that wins that and the director of that movie, there must be at least one such director, okay? And that director must satisfy this shape, which is Academy Award winning director, okay? Okay, we have a name and a date of birth, as we've seen before. But what's interesting about this is that this director must have an inverse edge win person from an Academy Best Director. So what does this mean? It means that the director of the movie associated with the Academy Best Director, that director must have won Academy Best Director, okay? So we don't know if it's actually the same one, right? We're not saying it's going to be the same award. Intuitively, we would expect that to be the case, right? But we're just at least constraining that that director has won an Academy Best Director, okay? So how do we specify that? We have Academy Best Director here, and we want to specify this forward edge here. So we write path win movie director in a list, and this will be win movie followed by director. And then we say that it must satisfy Academy Award winning director and at least one such value, as at least one such indirect director. So this is essentially expressing this path here. We see that we also have paths that we've already seen in the examples for all the property shapes. So in this case, we have a path of name here. We have a path of date of birth for here. The more interesting one is this one here, which we express as a path, which is the inverse path of win person. This means inverse, going in the other direction, in the backwards direction. And we have at most one of those. Okay, so we say that this Academy Award winning director has, at least one, has won at least one thing that satisfies the Academy Best Director Award. Okay. So what about this example here? Well, this will be targeted because it's of type Academy Best Director. Is it valid? It's valid. Okay, so how is it? Why is it valid? So we see that actually in this case, we're not asking for names or anything in particular. So this is the Academy Best Director, and we would expect there to be at least one value for Win Movie Director. So let's find Win Movie and then Director, okay? And that director must have a name and a date of birth, okay? That's cool. And as well, that director must have an incoming edge win person from something that satisfies Academy Best Director, okay? So we come back to here and we see that it's satisfied. So we're good. Okay, so another example, we would expect if we have this previous award edge, we would expect that the previous awards for Academy Best Pictures are themselves Academy Best Pictures, and so on recursively. Okay, so this means a recursive path of zero or many. Also the inverse previous. So if we go in the other direction of previous, we would also expect that would mean future awards to be of the same type. So this is what we're defining here. And we would expect at least one of these. This is okay because even the first movie will have at least one because it's a zero or more path. So it means that the node itself is in the path. So the very first Academy Best Picture will still have one zero more path of previous. And we see the definitions here. So zero more path previous, in this case, path zero more path of the inverse path of previous. Okay, so we see how we can express these paths in Turtle. So we have a graph here and we want to know, is this valid? So essentially what we're asking is, first of all, we have to, to make sure that all the previous things satisfy the shape, which requires that there's the RDF type Academy Best Picture and that it has 1 year. Okay, so one type, which is Academy Best Picture, and 1 year. And we see that everything has 1 year, everything has type Academy Best Picture. It's looking pretty good. And then the cardinalities. So every one needs at least one. So we see that everything has at least one. An interesting case is here, but because it's a zero or many path, it itself is included in the path. So that's also fine. Also this one here for the inverse one, the same applies since it's a zero or more path. So it's valid. Okay. So next we move on to the constraints. So we've seen how to target nodes. We've seen how to define paths for property shapes. And these are essentially, these property shapes are the things that connect the different shapes, right? What about core constraints? So what kinds of things can we constrain in these in SHACL and in shape languages in general? So we have these two different types of shapes. We have node shapes and property shapes. So when we define a shape, excuse me, so we have a node shape, essentially then we require that all target nodes for that shape satisfy the shape, okay? When we have a property shape, we have a shape and we have a path. And then we say that all the value nodes connected by the path E from each target node satisfy the shape. So the notation I'll use here is this, which indicates the value nodes. It indicates essentially the nodes connected to N by a path of E, okay? So we'll see examples of that. Or maybe just to go back here, for example, let me go to here. So for example, we have a movie and then we have a path, which is director, okay? So for example, here, this is the movie and then the path, essentially the value node on for a path of director would be bone, okay? So this gives us some notation to indicate for each node that we're targeting what nodes are connected to it by the path that we specify on the property shape. Okay, so we take an example here. We have movie is a node shape and we have a path year, okay? So within that we have a property shape path year and then we say that the years must have the data type G year. Then we have awards. Awards are also node shapes. So we have path year again, but this time we require that they have at least 1 year. In this case, we have Academy Award. We say that it must satisfy the node shape award. And then we have path, a property shape, where we say that we have the path win movie. It must satisfy any values, must satisfy the shape movie, and there must be at least one movie that is one. Okay, so let's take an example and look at this. So what do we have here? We have only one target, which is Academy Award is targeting the class Academy Award. So we get these as targets. Why do we get these as targets? Because they're all instances of a subclass of Academy Award. So we've highlighted the target nodes here. So the question then is, which of these satisfy the constraints we have here? So let's look at the first one. So it's targeted by the Academy Award. So first thing we say is that it has to satisfy the award shape. And the award shape says that it must have a year, which is a G year, and it must have at least one such thing. So we see we have a year, we have at least one, and it's the correct data type. So it looks good. Next one here. Sorry, okay, so it looks good from that perspective, but it also has to satisfy this property shape. So it says property, path, win, movie, node, movie, and min count one. So we would expect at least one movie to have won this award, but we see we're missing that. Okay, so this does not satisfy. Why? Because it doesn't satisfy having at least one node connected to it by win movie. Okay. So the next one here, we have a year, which looks good, except for, okay, one small problem. This is XSD int, not XSD G year. We see it has a movie, however, but it's already going to fail because it doesn't have the correct data type. Here we see something very similar to the first case. It doesn't have a movie that's won it, it's failed. Here we see it has a movie and a year. The year looks good and the movie looks good. Okay, so we have at least one movie. The last thing we need to check is that the movie satisfies the movie shape. So if we look at the movie shape, it says that any year it has must be of data type G year. However, it doesn't specify a min count. So it doesn't say that it has to have a year. So actually this satisfies this shape by not having any year. So everything is satisfied here and we're good. Last but not least, what would you guess? Will we pass this here? The answer is no. Why not? Because it must satisfy the award node shape, and the award node shape requires that it have at least 1 year. So we can also define shapes that are combinations of other shapes using Boolean combinations such as negation, disjunction, conjunction, and exclusive disjunction. What do I mean by exclusive disjunction? So if we have n shapes, it has to satisfy precisely one. It can't, if we have 5 shapes, for example, it has to satisfy precisely one of those shapes. It can't satisfy 3 shapes, for example. So we can define more complex shapes by these sorts of combinations. So let's look at an example. We have the Academy Award for Best International Feature Film, which is quite long if you write it out fully, abbreviated it slightly. So this is targeting a class by a similar name, okay? Recalling that we use S here to distinguish the shapes from the classes. So we have a property shape, which says that we have the path win movie. And intuitively, what we would like to say is that the movie that wins this award cannot be from the US, and it must be a feature movie. So we define up here what it means from the US. So it means essentially that there is a country. It has the value US on the path country. What does it mean to be a feature movie? It means that the path short, it has the value false. Okay, so it's short is false, which means that it's not a short movie. And from the US, country has value US. So what we're defining here is we're using these Boolean connectives. So we're going to say that this movie is an and, so it must satisfy these 2 shapes in here. It must satisfy that it's not the negation of from US. So we're saying it's not from the US, and it must be a feature movie. Okay. So we take some examples. So we see here that we have this movie, which is of type Academy Best International Feature Film. These are the 5 that are targeted for Academy Best International Feature Film. So now we need to check the property shape with the path win movie. So we're interested in the movies here. So we look at the first movie and we expect that it's not from the US, but we see it is from the US. So already this node will fail, right? Because its movie is from the US. What about this one? This one is from the US, but it's also from France, okay? But since it has a value, okay, has value US for the path country, it also fails, right? So this award fails because its movie is from the US. What about this one here? We don't know of any movie, or sorry, we have a movie, but we don't know what country it's from. So that's actually okay. So long as it doesn't have the value US for country, then we're fine. However, it also has to satisfy feature movie, which means that it must have the value false for short, which it doesn't, right? So this one also fails. What about this one here? We see that there's a movie from France and from Italy, and it's false for short. Okay, so it's a feature-length film. So this one is fine. On this last one here, we see that it's missing the short. So we don't know for sure if it's a feature movie, so it will fail. Okay. So what about value type constraints? So we can specify certain things on nodes. These nodes can be either the nodes of a node shape, or they could be the values of a property shape, right? The things at the end of the path. But in general, we're just going to talk about nodes. Okay. So for each node, what we want to say is that each of them is an instance of a class C. So we can constrain some nodes to be all instances of class C, to all have a certain data type D, or to be of a certain kind. So what do I mean by a kind? I mean like a blank node, an IRI, a literal. We even have these options of blank node or IRI, blank node or literal, IRI or literal. Okay, so we might ask, why isn't there blank node or IRI or literal? Because that would be equivalent to no constraint. Okay, so we have an example here where we say that a person is a node shape, and we're going to say that all of them should be of type person. And we're going to say that they should all have, they shouldn't be literals effectively. They should be blank nodes or IRIs. And we're going to target the objects of win person in our data. So let's take a graph here, and we're targeting the objects of win person. These are all the people here we're targeting. So we can run through them and see how we go. There is an additional restriction here that they must have a name that is a string data type, and it must have at least one name that's a string effectively. So we see that this person here is a blank node, which is fine, has a name, which is fine, and is an instance of person. So looks good. We see that this person here is an IRI, has 2 names, and is of type person. So there is a slight complication here that this name isn't really a name, right? It's an int. So here again, we're not counting how many things are strings. We're saying that all of the names must be strings, okay? And it must have at least one name. So this is going to fail. This is a string, literal, whereas the person itself must be a blank node or an IRI. So this will fail. Here we have 2 names, and we have a person who's an instance of person. So this looks fine. Finally, we have someone who has a name, but isn't an instance of person. Needs to be an instance of person due to this class person constraint. Fails. Okay, so we can define some values as well. Some details about the types of values that the nodes must have. So we could say for each node n, it holds that it has a value of min inclusive m, max inclusive m, min exclusive m, max exclusive m. So it's important not to confuse this with counting. This is not counting, this is defining the actual values of the nodes. So it might be clearer with an example. What we're going to say is that the Academy Best Picture targets the class of the same name. The shape targets the class of the same name, and it has a property shape where we're going to say that essentially the year must be 1929 or later. So it can be 1929, but it can be 1930, 1931. It can't be 1915, for example. So this was the first year of the award. I think it was actually 1927 or 28, but okay. So how do we proceed here? So we've got, again, we're targeting instances of Academy Best Picture. We have those highlighted conveniently. So we need to go through and have a quick look and see if they satisfy the shape. So we're saying that their year must be at least 1929, and it must be a G year data type. So this one looks fine, as it's min inclusive. If it were min exclusive, this would fail. 1930, we see year 1930 here. That looks fine, except for the data type is incorrect. So this is going to fail. This one here looks like we're going to have a problem because this is below the min inclusive value. So this is going to fail. This is going to pass. And this one has no year. Is that a problem? We haven't specified a min count here, right? So it's fine. Okay. So if it had a year, then it would have to satisfy these constraints, but there's nothing to say that it has to have a year. Okay, so there's two other ways we can define some constraints about what the values are. We can say that something has to have a value, which we actually saw in an earlier example already, or that it has to be one of these values. So we can specify some list of values for that. So in this case, any node must be V, and in this case, all of the nodes must somehow be a subset of the set of nodes that are defined here. So let's take an example of has value US, right? We already saw this, so we can go quite quickly. So essentially, we have our target nodes here, and we're saying that essentially the country they're from must have value US. Otherwise, they will fail the US movie shape. So this one has country US, so that's fine. This one has country US, also France, but that's fine. No, this one has no country. This fails because it has to have a value of US. So this sort of almost, it's not that it almost implies, it implies a min count of 1, right? Because it must have at least one value to have that value. This one fails, no country US, and this one fails, no country US. Okay. So we have string-based constraints. So if we have string values, or even they don't have to be strings, we can extract the strings from IRIs, we can extract the strings from numbers or from years, whatever we would like. We can then apply constraints on those string values. So we can apply a min length, a max length, or we can apply a regular expression. So we can check a regular expression P, and we can also add some additional flags. Your typical regular expression flags like case sensitivity is the most common one. So we'll take our example here where we have a node shape defined to be the modern year since 1900, let's say, I think. We're going to target, the shape will target the objects of the property year. It will have, we're going to require that they have the data type G year, that they have min length and max length 4. So they have length of 4. And that they satisfy this pattern, this regular expression, which is it starts 19 or 20, followed by any number, followed by any number. So a year from 1900 on to 2099. And we have a flag here to indicate case insensitivity, which is absolutely useless in this example, but I just wanted to show how the syntax looks, how you would write it down. Okay, so let's take some data. We're going to check each of these to see if we're fine. So this time, since we're targeting the objects of year, and this is a node shape, what we're actually targeting are the years themselves. We're targeting the nodes that represent the years themselves. So target objects of year, so we see that we're actually targeting these objects here. This one, does it pass? Yep, looks good. This one, does it pass? Well, we've specified that the data type is G year. If it weren't for that, it would pass, but in this case, it's not going to pass. This one, does it pass? It has min length 4, max length 4, that's all fine. It doesn't satisfy the regular expression because it starts with 0, 9, not 1, 9 or 2, 0. Fails, and this one passes, no problem. Okay. So we also have some constraints for languages. So the first one is that we can somehow define a list of permitted languages. So essentially we say that the nodes have to have a language tag that matches one of the language tags in the list. Or we can say that a particular node must have unique values for a language tag. So the intuition behind this, it might not make much sense, but it's essentially the idea that you might have multiple names for something in different languages, but you shouldn't have maybe you'd like to define this. You don't want to have multiple names in the same language. That might be considered redundant. So or maybe you have something like a preferred label, and you want to say that you only have one of those per language. So we'll take the example here. Movie has unique English-Spanish name, a very creative node shape name. So we're going to target the objects of win movie, and we're going to say that there's a property shape on the path name, and we want that the language is in, there's a small typo here, this should be G-U-A-G-E, sorry. One of the languages either Spanish or English or matches one of these. So it will also match, for example, Chilean Spanish. And we'll also add the restriction that of unique language. Okay, so we can't have two names with the same language tag. So, okay, this one here has no name. So do we need a name? We haven't here specified min count anywhere. So, okay, these are the nodes we're targeting. These are all the objects of win movie. So this one has no name. Is that an issue? No. So we're fine. Yeah, we don't have min count 0 here anywhere. Mr. Vincent, we have Senor Vincent and Mr. Vincent. I think it's Monsieur Vincent, and I think it's a French movie. In any case, does it satisfy? We have each of these languages seems to be satisfied or contained within the list of options, and we don't have two names in the same language, so yeah, looks good. Bicycle thieves. So we have no language tag. Since we have no language tag, it doesn't satisfy. It's not in the list of options here. So this will fail. This one here, we see that both of the language tags will actually match. They will be satisfied here. So that's fine. The only problem is that it breaks the unique language constraint. So we see that we have two names in the same language. So this fails. And this one here, we see that it's going to fail because we have Japanese, which is not one of the alternatives that were allowed for the language tags. Okay, so we're nearly there. So next we have cardinality constraints, which allow us for a given path E. So this has to be a property shape. For each node N, for a given path E, there are at most M nodes connected to N through the path E. Okay, or there are at least M nodes connected to N through the path E. So we also have these qualified min count where we additionally specify a shape. So then it's quite similar. We have at least M nodes connected to N through a path of E, but they must satisfy the shape. So if they don't satisfy the shape, we don't count them, okay? So it might have even more. Okay? And we have a qualified max count. So let's take an example. We've already seen a bunch of examples of max count and min count. So even here, sorry, there's a max count of 0. Okay, so we're going to take a slightly different example here. So what we're doing here, let me get up the graph, is what we're going to say is that if we have a list like this, then intuitively, there must be one node that satisfies having 0 previous edges. So there must be a first in the series, and we define that here. And we say that the first in the series has 0 previous edges. Okay. And then what we're going to say here is we have Academy Best Picture targeting this class here. So we see that all these nodes are targeted. And then we're going to say on the path of 0 or more previous, yeah, that each of these Academy Best Pictures has precisely one first in series. So it has precisely one in this path that has no previous path. Okay. So since we define 0 or more path, again, this node is included in the path of itself. So it itself also has one previous. So we can go through this and have a look. So this one here is satisfied. Like we said, it's the only node. Um, it's the only node here that's in a path of 0 or more previous itself, and it has 0 previous, so it satisfies this shape. So it has precisely one node that satisfies first in series in that from a path 0 or more prev. What about this case here? It itself doesn't satisfy the shape because it has more than one previous edge, but this one here counts as 1, so also is satisfied. It also satisfies Academy Best Picture. What about this one here? So we've done a little trick here. We put this nasty second previous edge here. So we see now that this one satisfies first in series, and this one satisfies first in series, and both of them are on a path of 0 or more previous, even though this one isn't a target, right? That doesn't matter. So we see it as two first in series, right? Two starts, start elements in the list. So it will fail. And if we think about it, this one will also reach here, and this one will also reach here. So this will also fail, and this one will also reach here, and this one will also reach here. So this one's also going to fail. Okay. So here we're just counting the first in the series. Here we're only counting with these qualified counts those nodes that have no previous outward edge. The first ones in the series. Okay. So we have two more categories of constraints. So second last category are property pair constraints that allow us to do some sort of comparison between the nodes on two different paths. So for given a path E, again, this will be defined on a property shape. For each target node N, it holds that equals F. So we give a second path, and what we say is that the first path and the second path, they must have the same values, right? So the nodes connected from N through E must be equal to the nodes connected to N through F. Okay. Or we can say that they're disjoint. No node connected from N through E can also be connected to N through F. We can also say less than. So we can say, for example, that all the nodes reachable through F must be greater, right? So the minimum of all those nodes must be greater than the maximum of the nodes in the E path. Or we can say less than or equals. Okay. So let's take an example. An intuitive idea would be to define that the Academy Best Picture Award should be awarded to a movie that came from the previous year. I'm going to slightly cheat. You could maybe think that in reality it would be less than or equals, but I'm going to slightly cheat here and say that it comes from the previous year. So if it's the 1930 award, the movie must come from 1929, 1928, 1927. Okay, so that's one thing here. The other thing that we're defining in this really quite complex path is that we saw these paths of previous through the awards. So if you go backwards through those previous, or you go forwards in the inverse direction through those previous, you would expect no award to have the same year, right? So if you're at the year 1930 and you go back previous 1929, 1928, 1927, you're not going to expect to see 1930 in that path. Similarly, if you go backwards through the previous edges to 1931, 1932, 1933, what you're saying here is essentially that in this path of previous in any direction and then year should be disjoint with year. So year being the year of the current award. So we say that these are disjoint. So we'll take an example, 1929. So we have to consider two things. So we again have the target classes here. We have to consider that the movie is less than year. The movie comes before the award, essentially. And we have to consider that there's no path that gives the same year of previous, an award in the same year. So we see 1929 is a unique year. There is no movie here, but we're not required to have a movie. There's no min count 1 here or anything like that. So we're fine. Yeah. So 1930, we have a movie. And in this case, given that we have a movie and it has a year, that year has to come before the award. But we see it's in the same year as the award. So this will already fail. Also, it will fail for a second reason, which we'll see. Let's look at this node first. So we see that the 1931 node has the same year as the 1913 one. So now there is a path through previous and year that gives the same year as the year of the award itself. So this is not disjoint anymore. So we break this one. So this one actually breaks both constraints because we've defined the inverse path as well. And we see that it has the same year as the award. So both this breaks both constraints. This one breaks the disjoint year constraint. What about this case here? We have 1932 year, and we have a movie. The movie doesn't have a year defined. So because it doesn't have a year defined, actually we're okay because there's no values here. So this is fine. There's no values on the path win movie and then year. This last one here, we have win movie and we have a year 1932, but we're missing a year here. Okay. So what happens in this case? This is fine again because essentially it's vacuously true. In the sense that there's nothing to break the constraint because the award doesn't have a year. Okay, last type of constraint are closed constraints. So we can say, for example, that only the properties in the shapes graph are allowed. So what does that mean? It's hard to formally define what that means. So it's better to look at an example. So we define Academy Award as a node shape, which targets the Academy Award class. And we have two property shapes, win movie and year. And we say then it's closed, okay? And we also give a list of ignored properties, previous and RDF type. What does this mean? It means that somehow if there's a property that's not mentioned by the shape, it's going to be a constraint violation. So if we have a property on Academy Award that's not movie, not win movie, not year, and not previous and not RDF type, then there's a problem. So let's look at this example here. Here we have year, so our only outgoing property, and that's okay here. So that seems to be fine. We have here win movie and year. We have here win movie and year, so that all seems to be fine. Sorry, we also have RDF type here and RDF type here, but that's in our ignored properties. So this one fails. Why does it fail? It doesn't fail for the closed constraint, sorry. It fails because of the data type. Yeah, so any year must be of G year, and that's not satisfied here. In this case, we have the outgoing property prev, which is okay. We have RDF type. We have two RDF types. It's fine. Doesn't matter. So we should be fine. Here we have win movie, and we have year, and we have type. We have prev. Again, that's fine. So we might suspect that there might be something wrong with the last example. We have previous, we have RDF type, and we have winner. But winner is not defined here as a property that's allowed. It's not in the ignored properties. It's not mentioned by the shape. So this winner seems to be indicative of a problem, of a constraint violation. So that fails. Okay, so these are all the core constraints that we have for SHACL. What else can we define in SHACL? There's a few other things. There's other syntaxes we can use and so forth. I'm just going to briefly mention one other feature we have, which are SPARQL constraints. So we mentioned at the start the idea that we could actually use SPARQL to query for constraints. And there are certain things that are not possible to express in SHACL directly. So for example, we might like to say that a movie, the movie winning an award is either from the previous year of the award or from the same year of the award. Okay, so we can't quite do that in SHACL to the best of my knowledge with the core constraints. What we can do is write a SPARQL query, and SHACL allows you to specify what are called SPARQL constraints, which are nothing more than SPARQL queries. So what does the SPARQL query do? It essentially queries for violations. So we're actually looking for the violations, the things that break the constraints. So what it gives us is a placeholder variable called this, and this will be replaced with every target node. Okay, so it will be in this case replaced with 5 values. Okay, and what we're looking for here, so for each of the targeted nodes, we're going to get its year as the value. And then we're going to follow a path of win movie year to get the year of the movie. that won that award. And then we're going to do a slightly complex, not slightly, quite complex filter here to check if the movie year plus one is not equal to the year of the award, or the movie year is not equal to the award. Again, we're looking for constraint violations, so we're looking for the bad cases, which in this case would be that if you add one to the movie, it's not equal to the award year, or if you check the movie and the award year, they're not directly the same. So that means it's either 2 or more years, or it's ahead of it's in the future of the awards. Okay. So what about, how did the constraints look here? What about here, for example? We see that essentially this won't be returned because it doesn't have a win movie, right? So this focus node will be, we will replace this with this target node here. Since it doesn't have an outgoing win movie edge, then it won't be violated, sorry. So results here will indicate the constraint violations, and this will be replaced with target nodes. So this I already explained. So this will be fine here. It won't be returned as a result for this query because it doesn't have an outgoing win movie edge, for example. How about this node here? Well, it has an outgoing win movie, and that has a year, and the year corresponds. So essentially it will fail this part of the filter here, the inequality of the movie year and the award year. So this won't be returned either. What about this one here? Again, this does not have an outgoing win movie, so it's not going to be returned. So let's do this one here. This one won't be returned. This one won't be returned. What about this one here? We have a year, we have a win movie, and that win movie is 1933. So here we might have a problem, right? So we see the movie came a year after the award. So this one fails. This will be returned from the results of this query. And the last one is fine because we don't have a year for the award. So we can specify also constraints in terms of SPARQL. That's the main thing here. In terms of what's returned, why do we return 3 things here, right? Why not just return the node that's breaking the constraint? The idea is that we want to return some report about what has failed. So essentially we return the path. In this case, there's a trivial path, which is year, and we return the value. What is the year of the award? The idea is that will be used, actually, these are standard variable names that will be used to populate the report to say what node, what path, what value it had. So this is required you need to return this for the reports. So that's pretty much SHACL. There's a few other bits and pieces, but that's the core of the SHACL shapes language. I mentioned at the start that there are 2 languages. There is another language called SHACL, which is a similar idea that expresses very similar features. One thing about SHACL is that it's not a web standard, but there is a specification, a formal specification there. There's people working on that. Both came out of the same working group. SHACL went towards recommendation, a standard for W3C, and SHACL was published in a different sort of fashion, such that it's not a standard, but there's a formal specification published with the W3C. So just to give a brief sort of flavor of what SHACL is or what it looks like, we don't have Turtle. This was one of the main divergent factors at the start, that SHACL was essentially going to be a new syntax that would be more intuitive somehow than what would be possible with Turtle. So you can maybe judge for yourself. So here's the shapes graph we have here, and here we have the definitions in SHACL. So we have a year, must have the data type G year. The default cardinality in this case is precisely 1, so we don't define anything more. We say that it must be 1 or more names, so from language strings. So we use plus to indicate 1 or more. We use star to indicate 0 or more, and here we say that judge must satisfy this shape. So this is a reference to the shape person, which is defined here. And scanning down along here, we see essentially, a similar pattern of what we define. We define multiplicities, we reference other shapes. Here we're referencing node shapes. Here we're also referencing node shapes, and so forth. So I think there's one small mistake there. That shouldn't be a semicolon. Okay, so this is SHACL. So I'm not going to go into detail because it's quite similar, and I focused on SHACL mainly because SHACL is a web standard. But SHACL is also quite widely used. For example, SHACL is used by Wikidata, who have started recently or in the past couple of years to define shapes for different types of entities. So we have, for example, a shape defined in SHACL for actors, where essentially we're saying that P31 is instance of human, so all actors must be instance of human. P21, I don't remember what it is, or P106, but I guess P106 must be acted in, or something like that. Or maybe not. Profession, I guess, might be. Profession, actor, or something like that. Okay. So we can define shapes, or users have started to define shapes for Wikidata to help to bring structure. So that's pretty much the story on shapes. It's an optional way for validating graphs. It's a optional validating schema for graphs, such that we can sort of have the best of both worlds, right? We don't have to have this, like in a relational database where you have to start by defining what are your tables, what are your columns, your primary keys, your foreign keys, and so forth. You can just start with the graph and just start defining nodes and edges and connect them however you want. But if you feel the need for structure, if you feel the need that you would benefit from having this sort of validating schema, you can have that at any point by defining your shapes. So yeah, I guess there's no questions as we're recording this offline. So yeah, this was the first time we taught this class in the course. So if you have any feedback or notice maybe any typos or that, and you can let me know. Okay.